So, I mean, to prove the NAC committee wrong, let us start a little on time. So we are very happy to have Dr. Aparna Taneja from Google DeepMind here. So Aparna has been, I mean, she's an expert in AI and ML in general, and would sort of say that, she's seen the field of AI and ML sort of grow. Like during her PhD at IIT Delhi, during a BTech at IIT Delhi, her project was on computer vision, where she was working on lane detection and so on when it comes to applications for automobiles. At that point, that's what the field was called, computer vision. And then so after her bachelor, she went on to do her PhD in Zurich, and where she worked on 3D modeling and so on. And then she joined Disney Research, after which she joined Google there and then has moved to India. And during her stint at Google itself, she's been worked on a variety of projects. So for instance, she was with the Earth observation science team, where they used to have the applications involved climate modeling and related problems. And then subsequently, she's been working with the AI for social good team in Google for the last about 3 years. So their group actually partners with a lot of NGOs across the world. So to name a few, there is RMAB, which is an NGO mostly based in Maharashtra. And there's also Kushi Baby that is based in Rajasthan. And there is Health Mum, which is based in Nigeria, where they handle questions involving maternity and child care there. So it's a great pleasure to have Aparna, and without further ado.
Thank you. Thank you for the nice introduction. Yeah, so today's talk is, I've just heard, based on our work using AI for improving maternal and childhood outcomes. Primarily, this work was inspired due to our collaboration with this NGO RMAB. They're actually headquartered here in Mumbai, and their mission is to improve maternal and child health outcomes for underprivileged communities. And this work has been done together with Professor Milind Tambe, who is a professor at Harvard, but he's also part-time at Google. So this is like work from our team at Google India as well as the extended team at Harvard. So just to give a brief intro into how this project came to being, I was just telling you as well that end of 2019 is when Google Research India Lab started in Bangalore. And so we, together with Google.org, which is the philanthropic arm of Google, we conducted this workshop where we invited NGOs and academics in the fields of public health, agriculture, and conservation. NGOs had to write proposals on the problems they were facing, academics similarly on their areas of expertise, and then we did some matchmaking between the NGOs and academics and funded some of these projects. So 6 projects were funded in the year 2020, and then 30 projects were funded in the year 2021. And since then, the program has now moved over to the Americas. And so RMAB was one of the NGOs that was funded in the first round, and the collaboration has been going strong. So they've been working with them since almost 4 years now. And they received they continue to receive funding from Google. And yeah, and we're a small team, so we weren't involved with all of the projects that were funded, some of them. And yeah, so RMAB has been one of those very amazing and rewarding projects. Okay. So if we come to look at the maternal mortality statistics, one of the goals set by the United Nations Sustainable Development Goals in the field of public health is that ideally by the year 2030, maternal mortality ratio should be below 70 for every 100,000 live births. Now, while that is true for most of the Western world, unfortunately, the numbers in India are significantly higher. In fact, currently in India, a woman dies in childbirth every 15 minutes, and 2 children under the age of 5 die every minute. And a lot of these lives can be saved only if women have access to timely and critical health information. And Dr. Aparna Taneja, another Dr. Aparna, she's the founder of the NGO RMAB. She has this wonderful quote, which is, "Pregnancy is not a disease. Childhood is not an alien. Dying due to a natural life event is not acceptable." So just to give you an idea of the scale and operations of this NGO, they're headquartered in Mumbai, but they're operational across 19 states in India. They partner with several NGOs, hospitals, They have trained over actually now 350,000 health workers and have served over 40 million beneficiaries almost. And they run a variety of mobile-based programs, both towards training health workers, ASHA workers across India, as well as towards generating awareness amongst women. So one such program is the mMitra program, which is based for women in Mumbai and its suburbs. And the program is targeted at pregnant women and new mothers, so women who have just recently given birth. And once you're enrolled into the program, you receive a pre-recorded automated voice message every week, timed according to your gestational age. So gestational age is how far along you are in your pregnancy. And these messages continue throughout pregnancy and up till 1 year after birth. So every week you'll get a pre-recorded message, and the message will be like, let's say you are 4 months pregnant, please remember to go for an antenatal checkup and keep taking iron tablets. You're 6 months pregnant, it's time for your gestational diabetes checkup. Or your baby is now 3 months old, reminder for their immunization and so on. So, the thing to highlight here is that this is really targeted at women from underprivileged communities. So this really is a very critical source of information for many of them who may otherwise not have access to such information. And in fact, the importance of listening to these messages has been shown to have great benefits on the health outcomes for both mothers and babies. Like 17% increase in infants with triple birth weight at the end of the year, and 36% increase in women knowing the importance of taking iron tablets, which is critical during pregnancy. However, despite the known benefits of having this knowledge, unfortunately, Arman noticed that up to 40% women drop off from the program gradually. So basically, they stop listening to the messages over time. And to prevent this drop-off, Arman deployed an intervention, which is basically a live service call. So a health worker from the support center will call the woman, so it's a live call, and she will try to understand why the woman is not able to listen to the calls. Is it like a logistic reason, the calls are coming at an inconvenient time, or is it, maybe the messages are coming in Marathi and the woman is a Hindi speaker or so. And mostly, however, it is more for them to explain to these women, to convince them the importance of listening to these messages. So they're motivated to listen. But you can imagine at the scale, population of our country, just this program alone, which is Mumbai and its suburbs, is enrolling 25,000 new women every month into the program. And obviously the NGO has a limited support center. So let's say if we can only make 1,000 calls, these are the live service calls. If we can only make 1,000 live calls each week, then the question is, which 1,000 women do we call? So this is similar to a limited resource allocation problem. The limited resource being service calls in this case. So just to give a hypothetical example, let's say we have these, women in the program, and orange indicates poor listenership. So they have not been listening to the messages recently, and green is a good listener. And let's say we can make 2 calls a week, 2 live calls. So we decide to pick the first 2 women at random. And now they both have started listening to the calls, and somebody else has also started listening who we did not call. This is just a hypothetical example. So we decide to call the last 2 women who are not listening anymore. And now one of them has started listening, but the other hasn't. So this is just to give you explain to you that just calling randomly may not be enough. Because you have such limited calls, you want to call them strategically to make sure you have the maximum benefit possible out of these calls. So this traditionally in AI has been solved using what we call Restless Multi-Armed Bandits. This comes from game theory where basically we have slot machines. Which slot machine do I pull how many times to maximize my chances of winning reward? So it's a similar problem. You have N arms. In this case, the arms are the women in the program, and you can only call K. You can only pull K arms. You can act on K arms, which is you can call K women at most every week, and your reward in this case is the listenership of an messages. So you can only pull K arms out of N, such that your listenership is maximized. And this is similar to your traditional stochastic multi-armed bandits. The only difference is that the word restless, which basically means each arm has a state. We define state is basically, in this case, whether they'll be listening to calls or not. So each arm has a state, and the state can change irrespective of whether the arm is acted upon or not. And similarly, reward is also accrued from all arms, irrespective of whether you acted on the arm or not. So we model each arm as a Markov decision process, and we simplify this to be a two-state, two-action problem. Two states are bad and good, so whether they've been listening or not listening to the calls, and the action is whether they will get a live service call or not. And hence, there's an underlying transition probability matrix to go from the bad listenership state to good listenership state with or without receiving a call. And if you know, let's say if you were to know these probabilities, then we can solve an optimization problem to see where we will see the maximum benefit of making a call. But obviously, these probabilities are not known to us in the beginning. So this was the first challenge. How do we learn these model parameters or these probabilities? This was our first approach that we built like 3 years ago, which has evolved since then. So we had access to historical data from the NGO. So we know a lot of women have been enrolled in the program. We have access to their call trajectories. When they get the automated call, whether they pick up or not, and for how many seconds do they listen to it or not. So we have access to that past data. We also have access to the demographic data. So when women enroll in the program, they'll give you some information like their age, education, monthly family income, number of children in the family, and so on. So as a first approach, what we did was we did clustering on their listenership behaviors, assuming that women who behave similarly will also act similarly if you intervene on them. So we did some clustering on their listenership behaviors and simple like K-means clustering, and then learned a mapping from the demographic data to these clusters. This we did so that because we trained the model on the past data. Now, when a new woman comes into the system, you don't know what her listenership trajectory will look like. But you know her demographic data because when she enrolls, she gives you that information. So given that demographic data, we can map her to one of these clusters, and we have probability, that there's a high chance she belongs to this cluster, and hence this is what her behavior will look like, and that gives us the transition problem. And once we have the model parameters, then we can solve the optimization problem. In this case, again, RMABs, there's this approach called the Whittle index, which is very popular approximation technique to solve this problem. Because otherwise, this is an exponentially hard problem because each woman, whether you call or not, you have to try options. So this is an approximation called Whittle index, which is popularly used. So once you have the model parameters, you can, this is like a predict then optimize approach, as we call them. First, you predict the model parameters, and then you use those model parameters to run an optimization, and then gives you this Whittle indices. Now, Whittle index basically represents the benefit of acting versus not acting. So it organically kind of gives you a ranking. The higher the index, the higher the benefit is to act on this person versus not. So if you can only act on key women, then you pick the top two to call. So this just shows the whole pipeline of that. For such projects where we collect the data, we learn these model parameters, run the optimization. The final step is to evaluate. And because we know this is coming from a real world problem, evaluating in simulation is not enough because that may not translate in the real world. So we did a real world field study with about 23,000 women. We divided them into 3 groups. Now, all 3 groups continue to receive the automated voice messages as per their usual schedule every week. But only 2 of the groups got the service calls, the live calls. So one group is the control group, the current standard of care, which is just getting the automated messages, no interventions. The second group was the round robin group, where you call them, this is what the NGO was using, like first come, first serve. Like if you enrolled into the system first, you will be the first one to get an intervention and so on. So you will get some K calls. K in this case was 225. So 225 service calls were given each week to 2 of these. And the third group is our RMAB group, the AI group, which received the RMAB-based interventions. And the study ran for about 7 weeks long. And then we monitored their engagement. That once these interventions are happening, is their listenership behavior changing or not? So we have access to their listenership logs. And the good bad is like a simple, the threshold that if on average these messages are like 2 minutes long. So if if they listen to over 30 seconds, we consider it to be a good listenership. Below that is poor listenership. So we monitored the engagement. This is a funny metric because we know that engagement drops over time. That's as we saw that gradually they listen less. We measure the cumulative engagement drops prevented compared to the control group. So the control group is the zero baseline here, and this is the engagement drops prevented compared to the baseline. So we see right from the start. So week 1 is where the intervention started, that the RMAB group seems to have leading to less and less drop-offs, which continues and sustains till 7 weeks. And the round robin group doesn't do so well in the first few weeks and then starts to pick up. So this is another example to show that just making these calls is not enough. You have to make these calls in a strategic so that you can make the maximum benefit of them. So we noticed that it was a 32% reduction in drop-offs compared to the control group. And it was found to be statistically significant. So then we thought this went wonderfully well, like surprisingly well. This matched exactly what we saw in simulation. So we wanted to deploy this system with the NGO. And so this system was called Saheli, so similar to Mitra Saheli, which is acronym for System for Allocating Healthcare Resources Efficiently Given Limited Interventions. And this is the plan that women enroll into the program. And we wrote basically a simple script on cloud that pulls data from the mHealth database, anonymized, call logs and the demographic data, generates these vital indices, and then integrates with the Arman's infrastructure and distributes these live calls across the health workers who will then reach out to these. But so no surprise, when you deploy something at that large scale, it rarely ever trivially, scales and works wonderfully. So we did a dry run before the deployment, and unfortunately, we were not seeing the same results we had seen during the real world field study just a few months ago. And so we did a lot of digging, and thankfully, we have a very good collaboration with the NGO. We have like weekly calls, so we were able to investigate together. So a bunch of things then had to be fixed. We did some more fine tuning of the model. Another thing was interesting was, so the app would, the list generation would take over an hour, and the NGO has limited compute resources. And whatever compute they had, if the script didn't finish in 1 hour, it would crash. And on cloud, they had whatever setup they had. So it had to finish in a limited amount of time. So basically, the goal was not only to have a good solution, but also an efficient, a computationally efficient solution. I mean, this is a limited resource environment. So it's like limited data, limited health workers, also limited compute. So you also want a solution which is actually sustainable for the NGO in the long run. So those changes had to be made. Then there was some unanticipated real world noise. Like finally, when we got down to digging and looking at the data, there were like weird spikes where suddenly listenership is very high and then lower. And then we found out together with the NGO that there was some power outage or something, and because of that, the data was not being so reliable. So then this had to be addressed. This is just to give you an example that it took us quite some time, and as researchers, we think all the exciting research problems, but to actually deploy it, you have to address all these real challenges as well. And then finally, a very important, particularly in this domain, is to follow responsible AI practices. So most big tech companies have their responsible AI guidelines, so does Google. So, which is one, the AI should be socially beneficial. Of course, in this case, we're trying to help marginalized communities, avoiding reinforcing unfair biases. I'll come to this in the next slides. And finally, anonymization. Privacy is very important. So we got all ethics approvals from ethics board to conduct the study, to deploy the system. All data was anonymized. There was no PII, personally identifiable information being used to train the models. And this data is never ingested ever onto Google servers. So neither the data nor the model can be used by Google. It's only for Arman, the data belongs to them, the models belong to them. So after following all of this, you are actually able to then deploy the model. And this just gives you an idea of the interface, like the health worker. When she gets assigned an intervention, she can see the details of that woman. When did she give birth and was she last called? What is her demographic profile? So that they can also initiate the conversation. They have some context about the person. So the fairness evaluation. So like I was talking about the second point, in this domain, I mean, in any domain, it is very critical, but in this domain, it becomes particularly important to ensure that there is no unfair bias against any community. So the NGO is also very keen on the fact that even though we know majority of these women in the program are all below the poverty line, but even then within that, there is quite a spectrum. So we have to ensure that there are no biases against any minorities. Now, we don't have access to sensitive attributes like religion, caste, etc. So as an approximation, we use the socio-economic indicators to measure how fair is the system. So we looked at the education and income as an approximation. So we did then analysis. This is a post hoc analysis of once the model was tested in the study. What did the distribution of the interventions look like? So if we look at the education, so orange shows the distribution of the whole population, the entire cohort of beneficiaries, and blue is the relative distribution across the interventions. So we see that more or less it looks similar to the distribution of the population. There's a slight preference for on the lower education side, but it's happening by chance. This was not designed to be so. So it's a good side effect, but yeah, this just happened to be so. So we see more or less it's similar to the overall population, just a slight preference on the lower education. Similarly, if you look at monthly family income, this is the spectrum of the beneficiaries. So you can see that majority of these women are really on the low income side. So the family income being between 0 to 5K per month, 5K to 10,000 rupees and so on. Again, we see more or less it follows similar to the population distribution, but it's doing slightly more on the extreme low income. And this was, like I said, this was a post hoc analysis. And now we're recently now working on a paper where we're explicitly including a fairness term in the optimization to ensure that the distribution of intervention is fair. Then we also, so we monitored the engagement, right? We saw the listenership behaviors were improving, but we wanted to understand exactly why did that happen. So we did the NGO did a survey where they reached out to 500 women who had received those live service calls. And of the women who had actually received a call and who remembered that they had received a call, they were asked this question that did these service calls really help you? And about 75% said yes. And then within those, we asked them, how did it help you? And some of them said, well, you know, there was an incorrect phone number or time slot. So one thing to note is many of these women don't have their own phone. So they have a shared phone. So calling them at the right time is very important. But majority of them said that it was because the health worker was able to convince us to listen to these calls. They explained to us why it's important to listen, and that's we started listening to it more regularly. So this model now has been deployed since over almost 2 years now, and we noticed there's a 130% increase in exposure to content in the bottom 25 percentile of users. So really, it's really benefiting the people who have most to benefit from such a program. And over 350,000 mothers have been served so far through this model and continue to do so. So this was then, so like I said, we noticed that the results in the real world deployment were not matching up to what we saw in the field study. So we kept working on improving the model. And one thing, so what we noticed was that if we look at the original approach, like I said, it was like a two-stage approach. First, you infer model parameters, then you run an optimization. So doing your two disjoint steps, right? So again, looking at a hypothetical example, let's say these are the demographic features and these are the transition probabilities on the y-axis. And high risk means women who are at high risk of drop off from the program. Okay, so those are in red. Now, if we were to do a two-stage approach where we're trying to basically learn the model parameters, no matter what method you use, supervised learning, whichever method you use, let's say if your goal is to maximize learning accuracy, most likely you will learn a model like this, right? Because your overall error will be reduced with a model that learns like this. However, your decision quality is now poor because your error on the people it really mattered is higher. So this made us realize that maximizing learning accuracy may not always be equivalent to maximizing decision quality. Now, our final goal is to have the highest engagement with the program. Our goal is not to learn the best probabilities. While it may seem intuitive that best probabilities should lead to the best optimal results, as we noticed here, it may not be so. And so we modify the loss function in our optimization to directly maximize decision quality. So earlier we were learning model parameters, then running an optimization. Now we run a joint optimization to learn parameters that will lead to the best engagement, back propagate, and so on. So it's now a joint learning on the parameters that will lead to the best decision quality. So now with such a method, you may learn a model like this, where your decision quality is now much better because you're learning more accurately for the high risk people. But your learning accuracy may not be as high because your average error on the whole cohort is now less. So then again, we did a field study because before we can deploy anything, we have to evaluate it in the real world. So we again did a field study, 9,000 women divided into 3 groups, control group, the original group, the original method, two-stage method, and now this decision-focused learning method. And we notice, as one may see, one may expect, since the two-stage method tries to maximize accuracy, learning accuracy error is lower for that method on average. But if you look at the decision quality, so the engagement, the same metric, listenership, engagement, drops, preventive, the decision-focused learning method does much better than the two-stage. And the study again ran for 6 weeks long, and we saw again that the new method was doing better than the previous method, and it continues to do so well after the study ended, which is great because we don't want a short-term boost. We want the effect to sustain. And then, so now when we talked about this work a lot, we're often asked, okay, the engagement has gone up. That is great. But how has it finally impacted the women? Has it done any health outcome measurement and so on? So we did another study to measure behavioral and health outcomes. Now, of course, health outcomes is difficult because many factors contribute to, let's say, the birth experience of the woman, the weight of the baby, and so on. So we try to measure at least changes in behavior. So we know that. So when we send these messages are sent to the women. We tried to so we did surveys, the NGO did surveys, both for antenatal behaviors as well as for post-birth. So like they would ask questions like, do you remember what was the birth, the weight of the baby at the time of birth, or what did you first feed to the baby, when did you first give the baby milk, or how are you feeding the baby, and so on. So basically trying to judge, trying to see, because you know that the listenership has increased, right, thanks to the interventions. But the question is, they've listened to the message, but have they understood the message? And then have they acted on the message, right? Because once they act on the message, that's a good behavioral change, which will hopefully then lead to a good health outcome as well. So they try to ask questions to basically gauge whether they actually listened to the messages, understood them, and then acted upon them. So those behavioral changes. And overall, we see that a higher gain in listenership typically led to improvement in behavioral outcomes as well. For instance, we saw greater family involvement. So 38% increase in women discussing the messages with their family. Because this is again often sent in the messages that, this is raising a baby is not a one person, it's a team job. So you have to involve everyone in taking care of the mother and the baby. Similarly, increase the knowledge about healthy behaviors for the baby. And as well as increase in knowledge about mother's health, because often post-birth focus may shift more to the baby. So the messages remind the mother that you have to take care of yourself as well while taking care of the baby. And we're now redoing this study on a more focused minority group to see if there are bigger, if you can see more substantial improvements. So this is a small clip of a video. So this work was featured in Google for India in 2021, also in IO Connect last year. And so this film was made for that, the short video I showed.
Now with AI, we can actually pinpoint which women
Double. And you can try it.
out of the thousands to pick up so that our health workers can reach out to them and help them access the service better.
मी तो फोन नव्हते ऐकत पहिला, त्याच्यानंतर मला त्या ताईंचा कॉल आला, त्या घरी आल्यात, मला समजवलं हा कॉल घ्यायला पाहिजे, तुझ्या पोरांसाठी चांगला आहे हा. मग तेव्हा मी कॉल घ्यायला लागले आणि ते कॉल ऐकून खूप बरं वाटतं की कोणीतरी घरचंच मला कोणीतरी समजवायला येतंय. मग जसं ते कॉल ऐकते मी तसंच मी माझ्या पोरगीचं संगोपन करते.
We've seen that when women listen to the information, the health outcomes are phenomenal. We're able to reach out to more and more women each week, get them back into the fold, and save lives because of AI.
And now, thanks to the encouraging results we saw from the mHealth program, we now want to scale nationwide. And this is made possible because now the government of India invited Arman to collaborate on this on the Kilkari project, which is similar to mHealth. It's again a maternal mHealth program. It's the largest maternal mHealth program in the world, and they have, yeah. So it's operated by the Ministry of Health and Family Welfare in partnership with Arman, and we again partner with Arman to hopefully see similar improvements that we saw with mHealth. So this program is operational across 18 states. A nationwide program. They have served already 32 million women, and it has 3.2 million active subscribers at any given time. So it's like 15 times the scale of mHealth. And in addition to the similar challenges that we saw in mHealth, lower engagement, high drop-off rates, we have far more challenges here due to the scale of the program. So one is regional variations. Somehow there are patterns, like different regions have different listenership patterns. This raises the question, does one model fit all? Do we train a different model for each region? We do not have, or there's very limited call center support. So we actually now have to rely on the ASHA workers to go and talk to these women in person, which becomes much more intensive. And finally, because of the scale of the program, we don't have access to demographic data of the women. And a lot of these women are from rural districts. They don't have, they only have limited access to a shared family. So we don't know if it's their own phone or a shared phone. And so we don't know what is a good time to call them. And moreover, there's also limited bandwidth on the system because right now, the government really wants this program to do well. And many women live in, like I said, they have either shared access to a limited access to a shared phone. They live in poor network areas, so the calls may not go through. So each call is attempted multiple times throughout the week until it's picked up. So right now, each call, so again, these automated voice messages are sent every week. This automated voice message will be sent multiple times, 9 times in total throughout the week until it's picked up. So a lot of bandwidth is being spent on just reattempts of these calls. If a woman does not listen to, I think it's about 6 to 8 weeks, listenership is below 25% continuously for several weeks at a stretch, and the woman is dropped off from the program. Because sometimes there are, wrong registration, there's the wrong number and so on. So they don't want to be spending bandwidth on sending 9 calls every week on a number that is not interested in the program or has been enrolled by mistake. So here, like I mentioned, there's no more demographic data. So we can't do that, what we did in our first approach, where we learned a mapping from demographic to listenership pattern. So now we only have access to the listenership data. And here, now we don't no longer use, like earlier we were modeling each arm as a Markov decision process. So their state depended only on the previous time step. Now we use the non-Markovian assumption. So we use time series data. For each person, we use last few weeks of listenership data to predict whether an intervention will help them or not. Like I said, limited beneficiary data, so we don't know their time preferences. So we're building algorithms to learn time preferences. And here, it's not just one intervention, we can potentially have multiple interventions. Because like a health worker visiting in person, like I said, is quite an extensive effort, right? Because it requires time and effort to reach each person. So we also want to use cheaper interventions like sending voice call reminders, sending SMSs, and so on. So multiple interventions. And like I finally said, there are system imposed drop-offs for poor listeners. So we really want to infer time slots and optimize the call planning to hopefully retain beneficiaries and potentially enable them to enroll in more beneficiaries. So the first one, the first model we built, like I said, since we don't have demographic data, we're now using time series of listenership data. So we use what we call TAR index. So it's the multi-action, MATARI, multi-action time series RMAB index. It's the LSTM based prediction. So given past few weeks of listenership data, we try to predict their future weeks of how much will they listen to in the future, and then how much will their listenership will be in future weeks if we intervene on them today versus not. And then again, try to basically look at who will have the maximum benefit of getting an intervention. So we look at the ratio of what will their listenership be if I were to intervene on them versus if I were not to intervene on them. And again, see wherever that benefit seems to be the highest will be the first priority of getting an intervention. So this, as of now, we've only run in simulation. We've not been able to do a field study. And in simulation, it seems to work much better than random, but there are no real world results. We're also working on building bandit algorithms for infinite time slot. So the first approach we tried was very simple. This is what is used by the model. Like what is done right now is calls are sent at random and time slots are not changed. Whether the call was picked or not, this information is not used. That's basically calling at random, no update. The simple baseline was you call at random, but you update. Every time a call is sent and it's not picked up, you get one data point, whether how likely it is for this person to pick up at this time or not. And the last was a simple, your traditional upper confidence bound algorithm. Keep updating your confidence bounds for a time slot with each data point. And already that approach seems to do in simulation much better. So we see that the mean average number of retries is much lower for a UCB based approach. Similarly, the number of people fraction converged is for how many people we are able to converge to the optimum time slot. And about for 80% women, we can do that within 6 weeks. But this is again in simulation.
So here the reward is the number of times it's picked up, is it?
No, the reward here is again the same, whether they listen to the call for more than 30 seconds.
Okay.
So we actually tried 2 versions in the next one. One was whether it was just picked up, and the other was it was picked up and listened to more than 30 seconds. So, and now we built a new algorithm on, basically, we don't have demographic data, but we have call listenership, again, patterns, right? And we know inherently there is similarity across users. People who have, let's say, shared phones, if their husband is working, they will have access to the phone in the morning or in the evening, so they're likely to pick up calls only then. Women who have their own phone are probably have equal likelihood of picking throughout the day. So we try to use this inherent similarity, and we try to use collaborative RL, collaborative reinforcement learning, to learn across these users. So think of it as a matrix. We have, in a matrix, we have, say, the women. So each woman is a row, and each time slot is a column. And we want to know for each woman, what is the probability they will pick up a call at a certain time slot. And when we start with only a few weeks of data points, we have some entries in the matrix, but we obviously don't know the whole matrix. So we want to do matrix completion. And for this, we use collaborative RL techniques. So one was doing some exploration exploitation. We explore for a few weeks, we learn, and then from there on, we use those time slots. Another was a more clever phased exploration exploitation, where you just learn for very few time steps, exploit it, do it again, exploit it, and so on. This seems to converge faster, but is more complex, expensive. So broadly, these are just collaborative RL techniques, and we notice that on average, so the previous approach was the UCD is the blue. So we see that regret is much lower for the matrix completion based methods compared to the upper confidence bound approach. And overall, in simulation, we notice a 45% reduction in the number of reattempts needed, and over 25% reduction compared to UCD for almost 75%. And so I've spoken a lot about this problem because we've been working on it for many years. And this work has inspired so many research projects within our team and within our extended Harvard team, like robust planning of RMABs. So we know that despite our best efforts, best algorithms, we know these signals are also noisy. Because a woman does not pick up does not mean she's not engaging, or because she picks up does not mean she's necessarily engaging. So we know there is noise in the system. So how do you do robust planning under uncertainties? So we did like an adversarial double oracle approach, that one is trying to make the worst case transition probabilities, and you have to still try to come up with an optimal solution. Then we looked a little bit at online learning. We looked at resource allocation within flexible budgets. So till now we had been assuming fixed budget, right? We can only make K calls every week. But what if this K was also something we can optimize for? Like I mentioned, fairness is in the works and many other research directions. And like we said in the beginning, this was not the only NGO we worked with. We also worked with other NGOs like HealthMAB in Nigeria. There again, so we noticed this limited resource allocation theme is a very common theme across several NGOs. So like HealthMAB came to us with a problem that vaccination uptake in Nigeria is very low, even though it's provided free of cost by the government. So again, they said that there were many reasons. One is lack of awareness. Women don't know that it's important to vaccinate. In some cases, they don't have the means. They don't have money to travel to the clinic or the vaccination camp to take the child. So it was a similar problem. They said we have some budget and different kinds of interventions. One is you send just call reminders to women, you need to remind them the vaccination camp is happening, please take your child. To some, they want to give travel vouchers, right? You can use the bus, the voucher on the bus to go somewhere. One was if they're living in a very remote area and a bunch of them are living there, they will conduct a camp in that. So again, the goal was how do we infer which woman, which intervention applies to which woman, such that it's within the limited budget constraint. So again, a similar problem. Khushi Baby is also working on maternal health. They are based in Udaipur in India. Yeah, so overall, we had been looking at, like I mentioned in the beginning, there were 6 projects funded in 2020, 2021. The goal was to look at all these interesting research directions in the fields of public health, conservation, and agriculture. And recently now, approaching the end, I've told everyone enough, but we now recently shifting our focus towards more foundational research in RMABs. So to build a foundation model for RMABs, such that right now, of course, we've done very nice work, which was inspired by our collaboration with RMAB. But we want to potentially then have this impact for many other NGOs. And by the way, all the code we built together with Arman, it's all open source, it's available on GitHub, and all the research is published. But we still want that it should be more generically useful. So you should have a more generic model that can then be fine-tuned for whoever wants to use this, like a limited resource allocation problem. So, inspired by like large models, the trend of large models, we want to build building a pre-trained foundation model, pre-trained flexible RMAB. Like I said, again, the inspiration was Arman and similar problems. We know that resource allocation is a common problem, right? You can have multiple actions, like we have a data set for COVID handling, where you can have multiple interventions, limited budget again. So we wanted to have a more generic model, which can basically work with multiple actions, and each action will have a different cost. Also allow for continuous and discrete states. So right now, like I said, we had in our Arman case, we had simplified the problem to make it, good state, bad state with a threshold. But listenership, for instance, can be continuous. Similarly, like in the COVID case, number of uninfected people or infected people can be a continuous state. So this allows to handle for both continuous and discrete states, as well as for a dynamic cohort. So when people are entering the system, people are dropping out of the system, so the cohort is also changed. So this will be presented at its trial very soon. And while a general multi-agent RL system may have complexity exponential in the number of agents, the way we train PreferMap actually benefits from a larger N. So just to quickly give a, if we look at the standard Bellman equation and we do the Lagrangian relaxation on the budget, so, this is your problem where you're trying to maximize. Are you all familiar with the concept of RL, the Q value maximization problem? So basically, it's a model-free approach. Q value means at any given state, if I were to act on them, what is the reward I hope to see in the future? And our goal is to learn these values such that I can conduct my actions to have the maximum anticipated reward within a fixed budget, right? The constraint being number of actions is less than equal to the fixed budget B. So when you do a Lagrangian relaxation, then you can incorporate that constraint within the optimization. So your B is the budget and lambda is your the deviation from the budget. And now, in this case, what we did was in the Q value, we also incorporated the features of the arms. So again, taking inspiration from collaborative RL, that similar people will have similar behaviors. This enables us to learn faster and across similar people using aggregate information. So if we were to do a Lagrangian relaxation, we can decouple the problem across users, and by exploiting similarity across features, we can learn faster. In this, we show in the paper that the generalization error actually reduces with increasing N. So now if new people come into the system who have similar features to what we saw in the training data, we can potentially predict right away. So this is what it shows. BDLPO was a model, was the state of the art, which was, so most applied methods would make some assumptions to simplify the problem. If you're looking at a very generic formulation of the problem with multiple actions, each action having different costs and so on, BDLPO was back then the state of the art, which was learning a model per person, individual. So then it doesn't allow you to do zero-shot learning, because now every time a new person comes into the system, you have to learn from scratch. While our model, having pre-trained it on a large enough data set for a new person, as long as the features are similar to what we saw in the data set, can potentially learn zero-shot, basically predict right away. So we just show that for different data sets, we require this method will require much less data to now predict on new people in the system. And this again shows that the performance is just as almost as good as what it would have done had it learned per person individually. And yeah, this just shows that we can. The black is the DDLPO, which does not apply when your arms are changing, while this method still works irrespective of whether people are joining or leaving the system. And the last bit, and then I'm coming to an end, I promise. The last bit is an extension we're working on. LLM is on the rage. So this gave us a nice idea that actually, again, inspired with our conversation with Arman, that different, we can train, let's say we can train a model and now we can run this every week to predict which women should be doing or which intervention should go to which women. But let's say, like we have the nationwide program, right? Requirements in Maharashtra may be different from requirements in Haryana. Let's say a program manager in a different region says, I want to prioritize younger women, younger mothers, or I want to prioritize low-income mothers. Okay, this would require you to retrain the model basically with a new reward function. So we wanted something that we can interpret natural language prompts to allow greater adaptability to changing goals, to allow for more flexible learning. And so we call this we changed the name now, it's a decision language model. So the goal was broadly, let's say, do efficient resource allocation, but let's say slightly prioritize younger mothers more. Now, prioritize younger mothers more, it's, mathematically it can be written in different ways. It's an ambiguous statement, right? So how do we decide which is the best way forward? So what we do is we take an LLM and we give it context. We give it full context that this is an RMAB problem where states represent good state is high listenership, bad state is poor listenership. These are the features of the women: age, income, education. This is the range. Age is typically 20 to 50, education lies in this, and so on. So you give it enough context and then tell it, this is an RMAB problem. You have to infer which intervention to go to which person while prioritizing younger mothers slightly. Now the LLM, because it has world knowledge, it understands what does it mean, young mother, right? It should basically, so it will infer which features that we gave it in the context are relevant to this prompt. So it will come up with some potential candidate reward functions. And then for each of these reward functions, it will simulate a policy. So like I showed in the previous slide, this new model that we built, the more generic model, in simulation for each of these potential candidate functions, it will simulate a new policy. And for each policy, it will generate a new reward distribution. That if I were to, let's say, act on K women for so many time steps, using this reward function, what will my overall results look like in the end? And then what we call in reflection, the LLM will do introspection on these reward distribution and compare it to the original prompt. And which of these seems to best align with the original prompt? Like if I had said younger mothers, it will look at how does the distribution now look like across age. And it will select the best function, use it as context for the next iteration and go. So this, with the help of the NGO, we ran on many use cases. We gave LLM many prompts to see how well it's working. So the baseline here is random. The yellow is base, that's the ground truth. So it's a human specified reward function. Let's say if we are saying, again, do allocation efficiently while slightly prioritizing older women, while slightly prioritizing low income women. So the prompt is mentioned on the x-axis. So the yellow is the human specified ground truth function. Orange is the default. Had we run our fixed reward usual policy training. Blue is no reflection. So the LLM comes up with one reward function and goes with it. And green is the reflection, where it generates multiple reward functions, simulates for each of them, compares them, comes up with the best one. And that's with reflection. So we see that in most of the cases, in many of the cases, we are almost able to achieve similar results compared to what the human manually specified a reward function. And this is just showing a variety of tasks to see how complex it can handle. So for instance, low income, the LLM understands from its foreign knowledge that which feature it should pull out to build a reward function. And obviously this is a single feature. So if you look at only the income, a task could also involve multiple features like low income and younger women. It will pull out the right features. An interesting use case is this one, early and late workers. Now this feature is not directly in the model. There is no such feature as their work hours. So we presume the LLM kind of infers based on their time slots. If they pick up morning calls or whatever, if they pick up evening calls and they're probably working during the day and so on. So this is an indirect inference. And in some cases, we see the reflection does not as good as the original, because sometimes just the one reward function candidate might be already good enough. And in some cases, we see it's not doing as well as the human, like technically challenged. Now, this is a very ambiguous function. A human may understand what demographic profile may be considered technically challenged, but for an LLM, this is not obvious. Yeah. Now I'm at the end. So I just said, just to summarize, we started with this amazing collaboration with Arman on working on the mHealth and the Kilkari program, which also led to amazing, research problems in the area of bandits, and published many papers. And now we're shifting more our focus towards more foundational genetic models in multi-region bandits. And I want to thank our collaborators at Arman, Google Research, DeepMind India, Harvard, Google.org, and University Relations at Google. Thank you.
Are there any questions?
So first question was, you use either the listenership outcomes or eventually some behavioral outcomes as a proxy for, ideally we would have liked to judge the performance of this whole system using health outcomes. But because, so one question is, what really are the challenges when you try to get your hands on actual health outcomes? And is it easier to deal with those challenges once you are working in a larger system? So in the Kilkari program, I guess now you have, you're working across a larger population and so on. So would it somehow be easier to get access to actual health outcomes, or what are the challenges?
Right. So I think in health outcomes, because a lot of factors contribute there, of course, not knowledge, your means to act on the knowledge, right? Like you may be aware that I have to take iron tablets, but can you afford to buy iron tablets? Can you afford to go for antibiotic checkups regularly and so on? Then there is also your genetics, right, which impact health outcomes. So a lot of factors contribute to it. And to be able to, really have statistically significant results, then you need to have a large enough population, enough diverse samples that you can then filter down on subgroups and say, okay, I can actually establish a correlation between this feature and this outcome. So that's the issue. And then you have to conduct that large survey, which is quite, like already just with the behavioral outcome study, we started with a very large set that eventually we ended up reaching out to very few women because these are low listeners, so they don't tend to pick up the phone that easily. They had to attempt like 5-6 times to finally be able to make a call. And so it's also hard for the NGO to make that. And for health outcomes, you need to do much longer analysis. It can't be just a few months, you have to observe it. Like it can't be just a child's birth date, because a lot more things contribute to that, right? What happened on the day of the birth, if they end up having a natural birth or an emergency surgery, and so on. You need to monitor more outcomes, which are milestones, over time. So that's a much longer commitment. So it's just harder to conduct this. With Kilkari, on the one hand, we have scale, you're right, we have much more data, but per person data is not rich because we don't have demographic data. So we have no background or no profile of the person.
So at some point, so when you were trying to understand, trying to decide which person to call versus not call, I think it was based on if you expect that intervention will make them increase their listenership, then you would
Right,
intervene.
right.
I was wondering if it's also likely that people for whom maybe because of their demographic, if it's highly unlikely that they will ever increase their listenership, then maybe they are actually the people who will benefit the most from intense intervention. So just I wasn't sure if what we wanted and how we were optimizing here matched.
Right. So right now, you're absolutely right. We are learning only on the basis of purely data. That if in the past you have this training data where you conducted interventions and you have now listenership behaviors of with or without intervention, and you learn the model based purely on that. It doesn't say, because it may happen that if an intervention did not seem to change a person's behavior, then this is what the model will learn. That the probability of this person changing behavior after intervention is low, so they may not get a call. Right? So somehow, so in the fairness problem, we are trying to look at it in that way to see how can we allocate resources differently while also maintaining a trade-off, right? Because again, there are limited resources. Like I said, majority of these women are below the poverty line. So they're all at a disadvantage already. But of course, you're right, within them, there's also a spectrum. So with this fairness problem, we're trying to see how to maintain that trade-off balance of getting value out of the interventions, but while also being fair to groups that may otherwise not get paid. So not an easy problem to, like, this is where we rely on the NGO's expertise to guide us. It's not something we
I had the same thought, and I was thinking if you collected the demographic data, then you could target those people who socially or culturally tend to just think of the ancient practices that these modern things are probably not fitting with their way of living, and they will benefit the most, even if they were given education. So they might need a different strategy. So if you collect the data, then you could target them with their specific needs.
So in the first program, the mHealth one, which is mobile-based, we have demographic data. We don't have sensitive activity, we don't have caste and all, but we have the demographic data like education and all, and that is all used in the model predictions. And like I showed that analysis that the resources are being given to all of them almost fairly and proportionally as per the population. Like I said, do we intentionally target more to the lower groups? That is something we are playing, that is something we are exploring. And this is why the language prompts work also sort of, so to give the NGO more flexibility to see how they would like to allocate the resources. Like I said, they are the domain experts, so rely on them to make that decision. So we can give them the tools, but ultimately they know the community best, they know what serves them. And also the health workers are doing a great job because they know these women. I think they almost know these women like personally because they engage with these communities a lot outside this program also because they're ASHA workers. So they are anyway visiting these women for like COVID vaccination, for polio, for many other programs. So they also have the right context of how to approach a person. They also understand the limitations of the person. So they will approach them accordingly.
I was wondering if the different parts of the aspects, how does the
Right. So all of this, the NGO is responsible for. We help with the wages assisting them in building the models, but ultimately it's the NGO that interacts with the health workers that they're onboarding and how to conduct these conversations.
So this entire process, you have any element of like feature selection or noise reduction? What kind of questions to ask the beneficiary?
Can you repeat?
I mean, so this is quite a broad question. I mean, in general, when we apply machine learning methods to the real world data is quite noisy. So
Yeah.
you have any stage of like feature selection or noise and try to
Right.
engineer the feature.
Right. So like I was mentioning the real world challenges for the deployment, we did a lot of model tuning. I mean, we started with some 100 features, whatever was available that the database collects. And then we did some, not manually, like just running, whatever, learning across hyperparameters, trying different feature combinations, and automatically then infers the whichever features contribute best to the result. For noise reduction, like I said, we explored this idea of the robust planning. So it was a method, it's like an adversarial method where we try to artificially give it the worst possible, like whatever transition probabilities you learn, it will add error to them. And now how do you adapt your policy such that you still are optimal and it keeps doing, it's like a adversarial kind of approach. We explored that in theory, in simulation, but we're not able to deploy it. It's quite a computationally expensive approach. We were not able to deploy it or evaluate it in the real world. But the advantage of this, so both in the clustering approach and the decision focused learning approach, because we're basically learning based on features and behaviors, and features match across. So we learn from aggregate data, it's not individual. So to some extent that helps with the noise. Because especially for interventions, even if you have 10,000 minutes or 100,000 minutes, intervention data is much less, right? So you already have much less data on the action samples versus the no action samples. But just due to the aggregation across women, to some extent that helps with the noise. But not explicitly that you're not doing that. I was wondering if you could shed some light on how the maximizing beneficiary quality was implemented over the learning activity. How was the rest? Right. So I didn't go over it in detail. There's the paper should be mentioned there. And here. This shows basically earlier we were trying to no matter which method you use, we were trying to optimize the accuracy, while in this case, it becomes a more complex optimization, and this was the difficult part, where you're trying to optimize the decision quality and with respect to the model. So then you break it up into quality with respect to Whittle index versus the model parameters. And this was the difficult part, and this is detailed in the paper on how, for instance, Whittle index is not differentiable. The version we were using was not differentiable, so we had to come up under some conditions, come up with a closed form implementation so that it becomes differentiable. Then top K, the decision quality, we were doing top K, right? Whichever is the top K is not differentiable, so we did soft maths instead. So these were it's in this, the paper is not linked here, but you have a AAA I-23K.
So, so one of the questions I was wondering is like, when eventually you are able to get through to a person who had no listenership and then we finally managed to get through, is there particular data that you would like to get from the interactions that work, where maybe the next time you can improve the, I mean, you can sort of use the automated voice messages itself rather than, because you know why exactly they were not listening. So is there a particular data you would like to get back from them that you can feed in?
Right. We talked about this. So basically there is no feedback loop happening right now. In fact, we're just having some discussions. Now there is this work happening on RLHF, right? Human feedback in the RL process, which is well, far from trivial. So one, we'll have to take, so that the health workers do make notes. After the call, they enter their notes in the system. So we do have some natural text, but you need to decode that and understand that. Yeah, we have thought about it, but it's not an easy problem. But you're right, we could learn based on the feedback on what typically is the reason. In fact, we had thought at some point to scale this, because this human calls can only scale so much, right? You can have 100,000 workers, even then at some point that's a bottleneck. So can we automate the process? So we had thought about doing automated calls. Like if we knew, for instance, for simple things like, like you get these calls from customer care. If, do you prefer in messages in Hindi or Marathi? And a person can answer, and this way you can solve that problem. Or do you prefer getting calls in the morning or in the evening, and you can update your system. But the NGO was very, they said that this is a sensitive domain, right? When the health worker calls, the woman ends up having a long conversation with the health worker about the pregnancy in general, like how do I know, how can I'm feeling this, can you guide me, or how should I approach the doctor and this and that. And there may be sensitive conversations as part of that. So they want the human element there to have that empathy. So a bot will not be able to kind of react in those situations. So if we knew confidently that it's a logistic thing, then we can do that. But yeah.
No, especially in the context of just even trying to figure out what is the right time to call.
Yeah.
That is something that, okay. So I was wondering, okay.
So we talked about that. So they said, yes, if you are confident that that is the reason, we can do that only that via an automated call, but the whole intervention cannot be automated, for instance.
So all of these models, they only take time as a parameter to say that whether this call was good call or a bad call.
Right.
Not the
Right. As of now, we just say if the person listened to a substantial part of the call, that's great. So it's a good listener, otherwise it does not. We don't know whether they act. For all I know, the child picked up the phone and listened to it. Yeah. So that's why it's also a bit noisy signal. Of course, if it's consistently happening, you know that this person is listening. But yeah, it's a noisy signal.
So for the
And that's why the behavioral study, to see really that it actually understand the calls.
For the element also, it did not depend on the demographic data.
For the element, sorry?
For the element part.
Yeah.
So we did not rely on the demographic data only through the call type. Was it?
So the LLM part of the model right now is only solving a small part of the model. So right now, in your RL framework, there's a reward function which says, which earlier was very simple, fixed. If a person is in a good state, listening, +1, if not listening, 0. And that's how you optimize, like you calculate your reward. The LLM only solving, tweaking that part, because I am saying that, okay, slightly prefer younger women. So it will say, okay, anyone who's in a good state, +1. And maybe if it's a younger woman, plus 0.5 extra, something like that. So you just keep tweaking just the reward function. The optimization, the learning, the policy will still do, the model will still do as it does always. As of now, the LLM is only tweaking that reward function. So it actually, I forgot to mention, we give it context, and what school is like, I mean, LLMs are crazy now, right? It spits out the whole code. So you can give it the whole thing that this is the RMAB, this is the problem, spit out the mathematical function corresponding to this, and it plugs it in, runs it fully on.
And that can generalize to, sort of other parameters in different states.
Yeah, so our hope was that we give more flexibility to the NGO, to the program managers, to be able to tweak as they feel necessary for a certain region, and it may be true for other domains as well.
Right, was the calls that get made, was there any has anyone ever thought about automating those, like using AI to the call calls themselves.
The automated calls or the internet?
Like the intervention calls.
Yeah, so like I was discussing, we did think about it to scale it. But there are sensitive situations like a woman may have miscarriages, right? Now, a bot cannot empathize, so a human will empathize and, give the person time on how to go forward. Similarly, other situations where you are asking questions, the time that this is something you should go to a doctor. So you can't really fully automate the intervention. If you know for sure that this is a timing issue, this is a language issue, this is a logistic issue, then potentially you can have an automated call. And our calls coming at a convenient time, yes or no, is this time better, yes or no, that you can do. But like we notice in the survey, majority of the women are saying that it's the health worker explaining to them that it's important to listen to the call. So that's more often the case for low engagement than the logistic. But you're right, if it was just the logistic reason, also one important thing is that the NGO believes that we shouldn't assume everyone is equally technically equipped or technically comfortable. So they want to keep it as easy as possible. They don't want to complicate things. Yeah. So person is overwhelmed. So you don't want to send calls and it says press 1 for this to keep it as simple as possible. That's also. But they are now rolling out a new program, which is WhatsApp groups. So not everyone has access to smartphones. Most of these women have, majority is still basic. Some have a smartphone and some haven't actually have data on it. So they're doing a now pilot with a small section with WhatsApp to see this kind of information. If there is a two-way conversation with a person can ask, but at a small section.
After data is mentioned day by day because of our awareness and all these things. So is there you are working on a pre-trained model or is there a sample complexity and you have introduced a DDLP approach. So how does it work?
So the DDLP approach, it was not ours. I was talking about this one, right? DDLPO was from a previous, actually at Middle Lab, a student who worked on this. This was learning a model per person. Sample complexity of that.
So to work on a pre-trained model, is it like to go with that or like we have to train the data again, maybe.
Right. So this I was saying the DDLPO was until now that was one of the models that had this generic capabilities where if you have multiple actions, which action were assigned to each person and each action has a different cost. It's a much more complex problem. DDLPO was solving that, but it was learning a model per person. With this pre-trained model, you can learn across people. So you can train it on a large data set of people, and then it will learn across these people. Such that now if a new person comes, and if it's similar to something I'd seen before, it can give it. And that is when I was talking about the sample complexity, that the more you really train, the better it will perform. So it benefits from a large.
I have this question. So I think there's a lot of noise if the ASHA workers have to call the right. So why don't there flexibility such that people who need such calls can call at a particular time slot, and then you can allot people to talk to them. Because you keep calling every night and call 9 times and they don't pick up the call time. Or if they don't have access to phone or takes time to speak.
Right.
Why is there no flexibility such that they can call and they are allowed the person to speak to?
Okay, so from what I understand, there are two problems here. One is, so I mean, Kilkari, this is the new, the nationwide program you're talking about, where we don't have the demographic data. So we don't know whether it's their own phone, what time slot is good to call them or not. just 3.5 million women. So it's not possible to call every person and ask, what is your time preference? And that's why we're working on algorithms to be able to infer that from their past listenerships to predict what will be a good time slot to call them. And what was the second part?
Why next will be something they can call you?
They have that flexibility. So there is a number, it's a service called missed call service. So when they enroll into the program, they are sent this number that you can give a missed call and a health worker will call you back. So they always have that option. So in this case, we are working with our initiative calls, but they always have that option of requesting a call back.
I was curious if since we're giving the LLMs directly to the managers that are managing the call, what is simulation like? Sorry,
This is all in simulation.
okay. So I was curious about what the safety measures are that's taken when you actually deploy.
That's a great question. So, yeah, that is something we're now actively looking at because LLM may generate anything, right? How do you ensure that it has not gone off too far or it has optimized is one thing at the cost of another? Like you said, prioritize younger mothers, but now it seems to maybe there is some strong correlation in the data that all the younger women are higher education. Now you're suddenly prioritizing a lot of higher education, which is not the intended effect. So we're looking at that problem now of introducing some fairness term or some regularizer to ensure that it still optimizes overall with a slight preference for what was the initial prompt so the results won't go.
Building on that, so the LLM is primarily trying to construct a loss function that sort of captures the notion of I want to prioritize blah.
Yeah.
Is okay.
Yeah.
So
So the reward function. The reward
yeah,
function.
the
that is
reward
shown
function,
now.
okay.
Yeah.
Okay, so the LLM is purely with respect to just constructing that reward function. Wise.
Yes.
Okay.
Earlier we had like a fixed function that good listenership is good, poor listenership is 0, and now it can tweak that and where everyone was considered equal. Anyone who is in a good who is listening well, it's a good reward. Not listening well, irrespective of what their demographic is 0. But now it can add that extra element that if you're a good listener and you're in this category, you get an slightly extra reward. So it will infer that.
I see. And I think you mentioned it in the talk, but maybe now I've forgotten. This thing about early and late workers, even though, I mean,
this to me also seems like a bit magic because it's not in the system.
yeah.
So we did it on the mHealth database where there is enough demographic data. So we do have information like in mHealth, women can fill out the time slot in the form. So there the time slots are known. So we figured that maybe it infers from that if a person is willing to listen to calls anytime during the day, then probably not working. If it's listening at certain times of the day, they're probably working during those hours, and that's why they're listening. So maybe it's trying to do some correlation like that. But yeah, that is something we should try. This is the thing with LLMs, the explainability is right now hard to backtrack as to how it came to that conclusion. So we're trying to also see this reflection thing, also how exactly it is comparing.
If not, let's thank Aparna again.